everyone, I'm Alicia, your MC for today's workshop. In this workshop, Zero to Hero-ish, your journey to car hacking begins. Division Zero's car security quarter core team, Alina Tan, Edmund Lim, Tan Pei Si, and Javier Yong will cover both theoretical vehicular knowledge and practical hands-on activities. Please welcome them.
Hi everyone, we are the car security quarter. So today I'll be presenting from Zero to Hero-ish, your journey to car hacking begins. So my name is Alina, beside me is Javier, bottom left is Pei Si, and bottom right is Edmund. So let's begin our presentation. Okay, so for today's agenda, we'll be talking about theoretical vehicular knowledge. So I'll be going through the introduction to vehicular architecture and technology, the overview of basic vehicular networks and protocols, and the introduction to vehicular track landscape and international vehicular standards. And then followed by Javier and Pei Si will go through the CAN bus protocol, CAN frame, the introduction to car hacking tools, and also the practical aspects for the session itself. And Edmund will be going through the rest of it: ISO-TP protocol, UDS, most lane FlexRay, and automotive Ethernet. Yep, so this portion as well, will be gone through by Javier and Pei Si. Okay, so basically, you can't see our faces now, but here's a photo of us in the top right-hand corner. So basically, I'm Alina, my teammates are Pei Si, Edmund, and Javier. So CSQ itself, we have a total of 20 plus members. We are also part of the wider cybersecurity community here in Singapore called Division Zero. And CSQ also powers the Automotive Security Research Group based in Stuttgart, the Singapore chapter, ASIG SIN. Yeah, so if you would like to join us, feel free to give us a shout out, and our Twitter handlers are right beside our names. Okay, so basically the goals of Car Security Quarter is to facilitate and promote automotive cybersecurity awareness to the community here in Singapore. We see that there is a lack of automotive knowledge around the community here. Hence, we wanted to empower like-minded security enthusiasts in gaining hands-on experiences, and ultimately want to contribute to the automotive security industry through our ground-up research, community engagement, and building of our test benches. Okay, so let's get started. This is an overall vehicular architecture of a modern vehicle, where you have a central gateway being linked to the central device. That's actually the majority of the components, such as the ECU, infotainment, OBD2 port, and telematics. So as you can see, the boxes marked in red are actually your aftermarket devices that can be connected to your OBD2 port or your central gateway. Your cell phones are also an external device that can be connected to make a phone call to your telematics itself. So majority of the architecture actually runs on CAN bus and LIN bus. However, in some vehicles, it will be a mixture of automotive Ethernet and CAN bus, or even LIN bus and other protocols. But we'll go through that more afterwards. Okay, so I will first start off with the definition of traditional vehicles. So basically, traditional vehicles are also known as mechanical horses that gets you from point A to point B. However, vehicles are essentially computers on wheels that have actually multiple embedded devices known as ECUs, electronic control units, that actually control different functionalities of the vehicle. So I would like to bring our attention over to the bottom right-hand side of the box highlighted in red itself. So the first ECU was actually created by BMW in 1939, and the CAN bus is actually, which is one of the most important protocols commonly used by vehicles now, called the Controller Area Network, was created by Robert Bosch Group in 1983, and the first connected car to feature connected functionalities was actually brought in by General Motors in 1996. So as we progress further from our traditional vehicles, we have our next generation of vehicles known as connected vehicles. So we actually commonly see connected vehicles on the road right now. So essentially, connected vehicles actually allow communication with external devices and have the capability of connecting over wireless networks. So some of these features are cellular connectivity, which allow manufacturers to push software updates via over-the-air channel. Unfortunately, this feature is not currently available in Singapore yet, but it's coming in the future. And then next we have the ADAS, which is known as the Advanced Driver Assistance Systems. which is actually designed to reduce human fatalities and reduce collisions. Something similar to like collision avoidance and cruise control that actually can be found in the adaptive features itself. Then finally, you have your in-vehicle information systems that actually allow a driver to make a phone call from their vehicle via their cell phone, voice control, and actually allow them to text messages or even check on the vehicle health via the vehicle diagnostic systems. Okay, so as we progress further with technology, we have the future, which is known as the autonomous vehicles. So an autonomous vehicle, which is short form for AV, so it actually operates via sensors, actuators, and algorithms. So ideally, we should actually operate it without any human involvement. There is also 6 levels of driving automation defined by the SAE, which is level 0, from fully manual to level 5, fully autonomous. So AVs have the following features. So basically, you have radars that actually monitors the position of nearby vehicles, video cameras that actually allow detection of traffic light and road signs, LiDAR sensor that utilizes light to measure distances and road edges, and then ultrasonic sensors to detect curbs and other vehicles during parking. And then we have the FMS, which is the fleet management system to actually control the fleet, which you don't see here. And of course, the software to actually process all of these sensory inputs to control acceleration, braking, and steering. Okay, so having mentioned on the evolution of vehicles, we now come to the communication protocols within the vehicle itself. So these are the common communication protocols within a vehicle. We have to actually secure it, if not in the proof as a potential attack vector for attackers. So firstly, we have the CAN bus, as I mentioned on my first few slides. So it's actually a message-based protocol that actually allows microcontrollers and devices to communicate between hosts in vehicular networks. Unfortunately, the CAN bus itself is very short, it's 8 bytes. So manufacturers have an improved version called the CAN bus FD, which is known as the CAN bus flexible data rate. It's an extension to original CAN bus protocol that actually provides accurate real-time data as well. And then we have the LIN bus, which is known as local interconnect network. It's mainly used in killer systems and other connectivity buses. My Edmund will actually talk about it more later. And then we have FlexRay bus. So FlexRay is usually used for critical systems such as brick-by-wire because it's high speed. And although it's very expensive, so usually you actually see it in higher end vehicles. And then we have the MOST protocol, which is known as the Media Oriented Systems Transport Protocol, which is commonly used in vehicle infotainment systems. Unfortunately, the MOST protocol will be phased out soon enough, but we still see some of the vehicles using the MOST protocol. Then lastly, we have the automotive Ethernet, which actually provides interconnectivity within vehicles. It's much lighter and faster than CAN bus. Again, Emma will be discussing more about this later in the presentation. Okay, so and then we have the several serial communications between the ECU, which uses the standard of J1708. Then J1850 is basically used for diagnostics and data sharing application using pulse width modulation. And then we have the SAE J1939, which defines the communication between nodes and used for vehicle diagnostics as well. And then we have the Keyword Protocol 2000, which is known as short form KWP 2000, which is used for OBD2 and covers the application and session layer in OSI layer model. And finally, the ISOTP protocol, which actually allows sending of more than 8 bytes of data packets over CAN bus, and it can allow the ability to actually chain the message into multiple frames, which actually allows a maximum payload of capacity of 4,095 bytes, a bit more than, even more than the CAN FD itself. So after going through all the commonly used vehicular protocols, if they are not scripted correctly, it will actually result in an increase in the amount of potential attack surfaces, which I'm going to briefly touch on over here. So firstly, we have the OTA updates. So attackers may be able to actually intercept traffic from the cellular channel and push malicious firmware in the vehicle system. As for the ECUs over on the right-hand side, they can actually include critical control units such as your PCM, which is known as your powertrain control module, your ECM, engine control modules, and the attackers are able to actually access through this OBT2 port to obtain information to the vehicular's internet network. Attackers are also able to do a man in the middle to obtain CAN bus data to control the vehicle if, let's say, the OBT2 port is actually blocked. So as for remote hijacking, we were on the bottom right-hand side, or vehicular theft itself. Attackers are able to clone key fobs by sniffing the signal sent by the remote and clone the frequency or perform a roll jam attack, which actually involves jamming the frequency and capturing the unlock key to unlock the vehicle. So for ransomware, over here in slightly in the middle, the attackers may be able to compromise the vehicle by asking for a sum of money to unlock the vehicle to drive, or even considering attacking the supply chain by installing ransomware on the manufacturers and tier one suppliers. Or attackers may be able to actually control the fleet management on the vehicular systems to actually attack the vehicle and control them, making them like botnets, and use it for distributed denial of service attacks. There are also actually different potential attack vectors such as spoofing attacks on LiDAR sensors, camera sensor attacks, and spoofing reverse parking sensors over on the left-hand side of the slide. Okay, so after touching on all the various potential attack vectors, here are the recent attacks that we've been seeing on connected vehicles. So for example, in August 2020, during a Black Hat security conference, the security researchers from the 360 group, SkyGo team based in China, have actually uncovered some security bugs that can remotely control some fleet of the Mercedes-Benz vehicles, for example, like starting of the engine. So in 2019, during the Black Hat conference, Tencent Keen Labs security researchers also based in China have discovered about 8 vulnerabilities 0 days in BMW that actually allow attackers to remotely attack the number of BMW models through various means like infotainment systems and BMW ports. And over here in December 2019, BMW and GT have allegedly been attacked by an APT group known as Ocean Lotus or APT32. So APT32 have infiltrated these corporate networks of these two manufacturers, supposedly to steal trade secrets and intellectual design for a startup company owned by the state nation itself. So earlier on, I actually mentioned some of the supply chain attacks. So one good example is over here. So in July 2020, the UK call center utilized by several car makers have actually suffered a data breach and over 500,000 customers were actually affected. So similarly, in 2019, 1 million customer records were stolen in Toyota's hack, which was allegedly conducted by APT32 as well. So although there hasn't really been a major cyber attack on these vehicles, it could potentially happen to our roads here in Singapore. And these are the attacks that we have been seeing for the past few years, with the most famous one being the Jeep Trophy attacks by the two security researchers, Chris Bellassek and Charlie Miller. And they were able to remotely control the steering and kill the engine at high speed. There were also zero-day vulnerabilities that allow attackers to tamper with the vehicle through BMW Portal and through these unpatched flaws in 2016. So in 2018, Tesla's keyless entry were actually vulnerable to a spoofing attack. Security researchers were able to clone the key fob by just walking past the owner. However, this can be resolved by adding a pin to the key fob itself. And then in 2019, Tesla's autopilot was compromised by Keen Labs researchers by using 3 stickers by tricking the autopilot technology and steered the vehicle into oncoming traffic. So earlier on, I actually mentioned the 6 levels of automation ranging from SE0, no automation basically, and to SAE levels 1 and 2, which features the ADAS and driver assistance systems. And also SAE level 3 and 4, which features conditional automation to high automation with a safety driver present in level 4. And SAE level 5 for full automation for fully automated vehicles. So level 4 itself, you still have run on geofencing. So as of now, we are currently at a state of SAE level 1 and 2. I understand that there are actually talks of releasing vehicles in the near future years on SAE level 3. However, as we progress towards autonomous vehicles itself, we unavoidably introduce new cyber-physical risks. So for example, long-distance remote attacks compromising the fleet management systems that governs the car code updates, and attacking the vehicle to allow complete vehicular control. And also for short distance remote attacks, one example could be attack against the tire pressure monitoring system, which is known as the TPMS, or Wi-Fi comms module. And then lastly, for the physical access attacks, planting a device that will inject arbitrary data messages into the CAN Ethernet network. Okay, so to address all of these threats that we see globally, different countries have various cybersecurity best practices and standards for the automotive industry. So in Singapore, we have the TR68, which is known as the Technical Reference 68, which addresses specifically on autonomous vehicles, specifically on Part 3, which focuses on the cybersecurity principles and assessment framework. As for the EU region, we have the ACEA's principles of automobile cybersecurity and NISA's publication on cybersecurity and resilience of smart cars. And as for ISO standards, we have the upcoming ISO 21434 road vehicles, cybersecurity engineering, and UN's take on the harmonization of vehicular regulations on WP29. And in the UK, the government published the guidelines on the key principles of vehicular cybersecurity for connected and automated vehicles. And in the US, we have the National Highway Traffic Safety Administration that came up with the Automated Vehicles for Safety article and the document of the FMVSS, which is known as the Federal Motor Vehicle Safety Standards, considerations for vehicles with automated driving systems. Although it doesn't really touch fully on cybersecurity, it actually touches on the research findings in terms of options regarding technical translations of the FMVSS and evaluates the regulatory text and test procedures. It actually briefly takes cybersecurity assessment into consideration. So, and also in the US itself, the Auto Isaac is also formed and they launched the cybersecurity best practices and guidelines document. So if you're interested, you can go to this website to check out more of these regulations. Okay, so after briefly touching on the global best practices and standards, let's deep dive into the international standards and regulations. So for WP29, it's actually created by the UNECE's Inland Transport Community, and it provides legal framework to allow contracting parties to establish regulatory instruments concerning motor vehicles and equipment. And as for the ISO 21434, it's a standard that actually addresses the management of cybersecurity for goods and vehicles. It actually set the minimum criteria for vehicular cybersecurity engineering and establishes guidelines on scenarios without a safety operator. And as for TR68, it's specifically for AV systems here in Singapore, and it establishes the cybersecurity principles and assessment framework to support the development and management for AVs. So the assessment framework actually acts as a guideline for AVs prior to actual deployment itself. So next up, we have the SAEJ 3061. It's actually a cybersecurity guidebook for cyber physical vehicle systems. It establishes high-level guiding principles for physical vehicular security. However, the 3061 will be superseded by ISO 21434 once it's completed. So currently, the ISO 21434 is in, I think it's in draft stage, if I'm not wrong. Yeah. And then lastly, for ISO 26262, although it's not a standard focusing on cybersecurity, it actually addresses the functional safety of the entire life cycle of the full vehicle subsystem for the whole subsystem of the vehicles itself. Okay, so next I'll be passing on my presentation over to Javier, and please will be talking to you more about the CAN bus protocol and the critical aspects. So I hope you guys are not asleep yet. Okay, thank you, Alina, for the question just now. So now I'll talk about the CAN protocol. So the CAN protocol consists of two portions. So one is CAN high and CAN low. CAN high operates at 3.5 volts and CAN low operates at 1.5 volts. CAN high usually operates at pin 6 and CAN low usually operates at pin 14 of the OBD2 port on the actual vehicle. So in this protocol, you won't really be seeing this portion, but if you do try it out on the actual vehicle, this is what you should be looking out for. The CAN bus carries 8 bytes of data, and CAN-FE is actually technically just an extension of the CAN protocol itself, so it carries 64 bytes of data. There's a differential signaling for fault tolerance. So for CAN high and CAN low, they will actually broadcast 1 volt higher or lower simultaneously as compared to like the resting voltage of 2.5 volts. It terminates after 120 ohms and supported baud rates are 125, 250, 500, and 1 Mbps. But usually it's 500 Mbps. And this is actually how a CAN frame looks like. So to break it down, there's a style frame, identifier, remote transmission request, data length code, data field, starting bit, and CRC. But what we really want to focus on is actually the data field. So we'll show you why in the next slide. Um, the data field is the data to be transmitted, and it's usually maximum of 8 bytes long. So let me just go to the next slide. So if you can see in this actual CAN frame, you see the data field is actually 8 bytes long, and you can actually see the interface and the CAN arbitration ID. So this particular interface is CAN utils. It's a live capture stream, and this is actually what you'll be interacting with later on during the practical itself. So SLCAN0 is the interface, and for the practical, you actually see it to be VCAN0 instead because it's a virtual CAN. And then the second arbitration ID and the data field. So let's talk about the car hacking tools that are commonly used. Here are the list of tools that you can use for CAN bus analysis. So what we're really using this time around is CAN details. And these are all the links towards for the different tools that you can actually use. And for simulation tools, there's UDS sim and IC sim. So CAN utils is just a socket CAN user space application that has multiple functionalities. Essentially, what you really want to do with it is that it can generate CAN data, it can replay the message that was sent, it can send messages, display CAN traffic, and yeah, you've actually experienced it for yourself later on. There's also CAN bus utils, which is similar to CAN utils, just as analyzing CAN bus traffic. There's also carrying carryable, ServiCAN, socket candy, and UDS sim, and later what we'll also be using is IC sim. So IC sim is an instrument cluster simulator for socket CAN, and it works together with CAN utils. So introduction to CAN utils. So the main functionalities of CAN utils is CAN dump, which is displaying, filtering, and logging CAN data to a file that is specified. CAN player is replaying CAN log files that you've recorded using CAN dump. CAN send is just sending a single frame of data. And then CAN gen is randomly generating CAN traffic. So this is actually really good for fuzzing, and you actually it's much more useful when you want to fuzz like actual like live traffic from car. CAN sniffer is displaying CAN data content differences. So when you later on the practical actually get to see like what you can do with it and what you'll be able to view with it. So now it's time for the practical. So let's see. IC-Sim is a software utility designed by open garages to produce a few key CAN signals to simulate an actual environment in the car, and that's the link where you can download IC-Sim from. And it allows you to practice CAN bus reversing in a very safe environment, so you won't be breaking any cars of your own. Anything that happens is completely fine. And you can also change the difficulty levels by adding, so you actually add more background noise, which makes reversing much harder to perform as you go along. And at the same time, you also have IC Sim, which is the instrument cluster simulator for socket CAN that works together with CAN tools. So this is the installation. So for all of you that's following the practical still, so what you want to do is that you want to update Kali Linux first or any Debian or Ubuntu VMs that you have or actual computer by doing sudo apt-get update. Or if you're using Ubuntu, just do the equivalent of the commands over here. So you need to install libsdl2dev and libsdl2imagedev libraries with the following command. And after you install those libraries, you need to install the CAN utilities by sudo apt-get install CAN utils. Then you also need to install ICSIM. So just git clone the GitHub repository, and then it automatically be cloned over to your home directory. And make sure that in root, this won't actually be able to run without sudo permissions. So just cd into the directory, and you should be able to see the contents of ICSIM if you just run ls. So we're just gonna give you 5 minutes for installation over here. Make sure you get everything up, and if you can't get things up, you can feel free to message any one of us to help you out with the installation.
thank you, Pesu, for the Canvas introduction. So now we'll be talking about the practical part of ICC and how to manipulate the Canvas packets. So firstly, what we need to do is to prepare the virtual CAN network and run the ICC software. So as mentioned by Pesu before, we need to git clone the ICC directory from the internet. So after you git clone, you should have the ICC folder in your Linux machine. So if you go inside, there should be a bash script called setup.weekend.sh. So what this bash script does is basically create a virtual CAN network called weekend0, and this virtual CAN network will basically help us simulate the CAN network and also help us run the instrument faster. So if we go to our our Linux machine, we can verify that the VCAN network is indeed installed by running a simple IP-A or ifconfig, and then the VCAN 0 network should be here on our device. So uh, we'll move on to the next step, which will be capturing the CAN bus traffic from VCAN 0. So what this slide is talking about is basically we need to start our ICC, and which is our cluster, and then we also need to start our controls, which will basically uh, send the manipulator packets over, and then we also open CAN sniffer to sniff out the traffic. Okay, so we can do this on our computer by running the binaries located in ICC directory. So the first thing is to run our instrument cluster, which is in the binary ICC vcan ICCM, sorry, and then with the argument weekend0 as our uh, network. So after we run, we should see this dashboard which has the speedometer and blinkers. Then the next step we should the next step to do is run the controls, which will send the packets to our instrument cluster. So this is the controls binary and how it should look like along with our cluster. So the last step is to run CAN sniffer on our device to sniff out the network packets. So CAN sniffer is already pre-installed, so we don't need to go to any direct path. So if we run CAN sniffer on computer, it should run out like this. So I'll stop CAN sniffer and move on to the next slide first. Okay, so the next slide will cover basically the various different controls that we can use on our that we can use to send to our cluster so that to manipulate the various car functions. Okay, so the first step to do is to dump our perform CAN dump, which basically listens to the network traffic, but stores it in a file in a current directory. And then on the right is basically the different functions and the different keys mapped to it. So like for example, accelerate is up arrow on your computer, but do remember that you need to click the joystick window and press the keys first, if not it won't work. So we'll move to the machine and see how it plays out. So first we run CAN dump, and then we'll listen on weekend0. So if you take note, uh, this what CAN dump does is basically save the CAN traffic to the file name which is on the terminal. And then if you click on the joystick window and then you press, like for example, up key, you can see like the speedometer increases. So likewise, if you follow the slide, left arrow is for left turn signal, and then right arrow is for right turn signal, so on and so forth. So you can try this out on your device and then see how it goes. Okay, so moving on, we have a CAN player, which basically reads the CAN dump file so that you can view what the CAN bus traffic captured earlier and see like it replicates whatever data you input and outputs out on the cluster. So it should basically replay the same thing as what we did earlier. Yeah, so if we go to our Ubuntu machine, okay, so on the Linux side, what we need to do is to run CAN player, and you need to add a -v, the flag, so that all the CAN data gets printed out at the same time. So when you run CAN player, like on the right, you can see like all the CAN data that was transmitted just now via CAN dump. And then we actually need to wait for a while to see the changes replayed on the IC simulator, because I actually started the CAN dump a bit too early. So if you wait for a while and look at the IC simulator, you can see the changes. As you can see now, the speedometer increases, and then followed by the blinker, and then there was the left blinker just now and the right blinker. So yeah, so that's template essentially is basically just replaying what you log inside the CAN dump, and then yeah, and then we'll move on to the next slide. Okay, so moving on, we'll be talking about reverse engineering the CAN ID from VCAN 0. So essentially, what we are trying to do here is analyzing the CAN traffic by using CAN sniffer, and then see what are the changes that are made to the traffic when we are using the controls to manipulate the data. So if we go to the Ubuntu machine and run CAN sniffer, as shown here, you can see that this is the CAN traffic currently displayed. So as mentioned just now, like for example, if you press up key, it's the speedometer will increase, right? You're supposed to look and analyze the 10 sniffer traffic on the right to see what changes. So I think speedometer is a bit hard to see. So we'll do the left blinker, for example. So if you press left blinker, you can see that I think 188 is changing from 0 to 1. Oops. Yeah, 188 is changing from 00 to 01 on the first byte. So that's how you see the changes in the CAN traffic. Yeah. So moving on to the next slide. Okay, so now you'll be tasked to do 3 analyses of how to reverse the CAN ID. So the first one will be acceleration and deceleration. Second one will be door open, door lock, and then the last one will be right turn and left turn blinker. Okay, so we will give you 5 minutes for you to try this out, and if you have any questions, can ask us. Okay.
We will leave it over here so that you are able to see what we wanted you guys to do. So yeah, see you in 5 minutes.
Okay, so welcome back, guys. So now we'll be going through the answers for the reversing CAN IDs question just now. So for the first one, acceleration and deceleration, it's CAN ID 244. So if you look at the Ubuntu screen, uh, yeah, so if you look at the Ubuntu screen, right, if I press the acceleration button and then you look at the CAN ID 244, it it increments by 1 bit until 38. Yeah, 38. So then if I let go of the deceleration, it decrements by 1 bit also. Yeah, okay, so next is the right turn and the left turn signal, which is Kennedy 188. So 188 is, if you look at the left turn, then if you look at the right side, it changes from 0 to 1 for the left blinker, and then for right, it changes to from 0 and to 2. So, and then lastly, for the door lock and door unlock, so currently, right now, the door is locked, and if you want to unlock it, it's Shift A for front left door. So if I press Shift A, the it changes from 0F to 0E, and then if I lock it again, it's 0F again. So yeah, that's so essentially like reversing CAN IDs requires like for you to analyze the CAN sniffer and the CAN traffic in order to pick out the various CAN IDs for the different functions of the cars. So now we'll be moving on to the next part of the practical, which is spoofing the CAN bus traffic from VCAN 0. So previously, we have already covered how to reverse engineer the CAN IDs. So now we'll try to spoof the CAN traffic directly using the CAN send tool. So CAN send requires you to input the network and also the CAN ID and along with the data. So we can try to edit the speed by sending the 11F6 data to the CAN ID 244. So if we go to the Ubuntu machine and try to send that, okay, so if if let's say the CAN send data is not replicated on the IC simulator, we can try to include a while loop so that it's sending the data continuously. So after creating the while loop bash command, you can see that the speed actually maintains at 60, and then yeah, that's how you basically like send like you spoof the CAN traffic and then send the data to the various CAN IDs. Okay, so next we have another level exercise for you to try out. So we have come up with uh, different parts of the different functions of the car for you to attempt and spoof. So first we have uh, increase the speedometer up to 60 miles per hour. Then secondly will be to bypass the speed limit. So that will be increasing the speedometer to 220 miles per hour. Thirdly is to keep both right and left turns at the same time. Fourth, keep the right turn signal up. Fifth is to keep left turn signal up. And then the last two will be to unlock all doors and to lock all doors. Yep. So We will be giving you around 10 minutes for you to try these various exercises, and then we'll come back and discuss how to tackle each of them. Okay, so welcome back, guys. So now we will be going through the questions about spoofing the CAN traffic. So the first one will be accelerating to 16 miles per hour. So we can do that using CAN send, and then for 60 miles per hour, the CAN ID is 244, and then the data is 23F6. So if we input that command into the Ubuntu machine, it will look something like this. Okay, so after you input the command, you also added the voucher, so it's more obvious. So if you look at the IC simulator, the speedometer will be at 60 miles per hour, and then I'll stop this process, and then we'll move on to the next one, which is bypassing the speed limit to 220 miles per hour. So for this, the CAN ID is the same, 244, because it's regarding the speedometer, but for data, it's 9,000. So we will change the last four digits to 9,000, and then you can see that the speedometer changes to 220. Okay, so next. Okay, next we'll be going through how to send the data for the signals and also for the DOS. Okay, so firstly we'll go through how to keep both signals, which is for signals is 188, that's the CAN ID, and then if you want to keep both signals up, the CAN data is 03. So if you go back to the Ubuntu and try, so I'll edit the command. Okay, so after inputting the command, you can see that both signals are now lighted up. Okay, so next question will be right turn signal. So right turn signal, we change the CAN ID remains the same at 188, but we change the CAN data from 03 now to 02. So after inputting that, you can see now that the right signal is turned on. Okay, lastly, for signals, we have the left turn signal, which we will change from 02 to 01. Okay, so that concludes for signals. So lastly, we'll be doing the DOS unlock CAN message. So for DOS unlock, the CAN ID also remains at 19B, but then we'll change the 0F data to 00. So if we input this, you can see that on the bottom right, the DOS are actually locked. So that concludes the practical portion for ICC simulator, and then now I'll be passing my time to Edmund. We will talk about more about the other protocols involved in hierarchy.
Thank you, Javier, for going through the lab work on the IC sim. So now I'll be going through the different protocols present in the vehicles. And the first up, we will have the ISO-TP protocol, and it's covering the layer 3 and 4 of the OSI model. It is the international standard used to send data packets over the CAN bus. So previously, Pacer has covered some CAN bus frames, and it contains 8 bytes of payload. With the ISO-TP, it can extend the limited payload to a data size of 4095 bytes. And the most common usage of ISO-TP is for the transfer of diagnostic messages with the OBD tool. So the structure of ISO-TP protocol mainly defines 4 frame types: the single frame, first frame, consecutive frame, and flow control frame. And they are denoted by the different codes in the first byte of the CAN-TP header. So packets containing up to 7 bytes of data identifies as single frame, and anything more than 7 bytes of data will go to the first frame, consecutive frame, and flow control frames. So how the communication of ISO-TP protocol works is the sender will send the first frame to the receiver, and the receiver will respond with a flow control frame. And then the sender will consecutively send frames based on the flow control frame block size and the separation time. So SocketCAN has actually some basic functionalities to use ISOTP tools, mainly ISOTP send, ISOTP sniffer, ISOTP dump, and many other functionalities. So this is an example of how ISOTP protocol can be used using SocketCAN and UDS. So the first one denotes the requested dynastic session code. And then like the CAN send, we have the interface, which is SLCAN0. And with the -S and -D flags, we can denote the sender and the receiver of the response and transmit. Okay. Stop. So moving on to the UDS, which is Unified Diagnostic Services Communication. The UDS uses the ISOTP protocol to send larger data outputs over the canvas. So the UDS is actually to provide a read-only view to display vehicle information to mechanics. And however, troubleshooting the vehicles, such as sending a request to unlock doors, can also be done using UDS. So UDS capable modules such as ECUs are able to respond to the ISOTP messages. Examples are your instrument clusters, and they provide the following functionalities such as the DTCs, diagnostic trouble codes, upload download capabilities for software reprogramming, remote routine activation to start a routine remotely, and also read-write capabilities to rewrite any EEPROM values. So the UDS has a specific method to receive response data. And like the canvas, it has the arbitration ID, a positive and a negative response. So at the bottom right, you can see an example of a negative response whereby a response is sending a 7F, and for the positive response, it will be adding a 04 hex into what you set up. And the structure of the UDS is as the example picture. We have the interface, the SLCAN0, the sender and receiver arbitration IDs, number of bytes, and also the payload. So that was the UDS and ISOTP protocol. Next, we'll be moving on to the FlexRay protocol. So in the FlexRay protocol, it is designed to be faster and more reliable than the CAN bus. And it's commonly used for braking systems or drive-by-wire systems. And it allows clock synchronization, and the common applications and critical safety components are high-performance powertrain, adaptive cruise control, drive-by-wire, and active suspension. So the downside of FlexRay protocol is actually the price is very expensive to use. So we don't really see it in normal vehicles and usually on the higher end vehicle models. So the structure of the FlexRay protocol can be broken down into the header, payload, and trailer. The header is 40 bits long, and it contains information such as the status bits, the frame ID, payload length, header CRC, and cycle count. The payload is 254 bytes long and contains the data to be transferred by the frame. The trailer contains 3 bits of CRC used for error detection. So the LIN protocol is actually the opposite of the FlexRay. It's a slower protocol compared to the CAN bus. And it's a low-cost serial protocol designed to interconnect other components, and it's meant to complement the CAN network within the vehicle. So it has a master and slave network topology, and similar to the CAN bus, it's using a broadcast network and utilizes the ISO 1797216. The common applications for the LIN protocol is, example, the steering wheel, door, seats, and air conditioning. So anything that is not critical or dependent on the speed of transfer, yeah, it will be using LIN protocol. Some of the hardware being used to decode the waveform of LIN bus can contain, example, logic analyzers and bus analyzers. So the structure of the LIN protocol, since LIN is using the master-slave architecture, The master node is looking through the snake nodes, pulling for information and transmitting the header of the link bus, and the slave responds with 8 data bytes. So the header consists of the following information: the sync break field, which indicates the start frame to all lane nodes, the sync bit, which allows the lane nodes to determine the baud rate used by the master node, identifier, which identifies the lane message to be sent, and the parity bits, which determines the validity of the ID field. In the response, we have the data field and a checksum. So the data field, it transmits 2, 4, or 8 bytes of data when the link slave is pulled by the master, and the checksum ensures the validity of the link frame. So in this table, we can see a short breakdown of the link bus, CAN bus, and flex ray. So the difference in the voltage, link bus is using 12 volts, and CAN bus is 5 volts, while flex ray uses up to 3.5 volts. Wires, link bus is using a single wire, CAN bus using twisted pair, and flex ray is using a twisted pair of 4 wires. In the speed, you can see that link bus is only 20 kilobits per second, CAN bus up to 1 megabit per second, and flex ray 10 times of that of CAN bus. So the cost for link bus is cheap, and CAN bus is moderate, but flex ray is very expensive. That's why we don't see much use of flex ray. So now I'll be talking about the MOST protocol. So MOST is Media-Oriented Systems Transport, and is actually used for multimedia to transmit audio, video via the plastic fiber optic cable. MOST ring daisy chain allows high-speed networking subsystems to be connected together on a multimedia network, optimized for multimedia and infotainment applications. For MOST protocol, it supports up to maximum of 64 devices in the network, and is used in almost every vehicle that requires multimedia. So the design of the MOST protocol, there are few masters that exist in the MOST network: the timing master, network master, connection master, and power master that serves different purposes. Within the network, MOST protocol has 3 communication channels, namely the control channel, asynchronous channel, and synchronous channel. There are 3 different types of data frames for MOST: MOST 25, MOST 50, and MOST 150. The difference between them is actually just the baud rate. So MOST 25 is using a 23 megabaud system, and MOST 50 is 2 times the speed of MOST 25, and MOST 150 is 6 times the speed of MOST 25. Most devices follow OSI model, with layer 1 handling the physical optical interface, layer 2 which acts as a MOST transceiver, most network interface controller, the NIC, layers 3 to 7, acts as a network interface and serves as a communication block for the application. For the communication of the MOST protocol, the MOST device consists of physical, network, and function blocks. Network service consists of the NIC. The function blocks on layer 7 application has a master and slave function. The function blocks uses functions in slaves called controller, and the controller sends commands to the slaves to receive data from the slaves. Controllers are connected to the HMI, which interfaces to the user to issue commands to the slave. So the physical properties of the MOST cable, they're using photodiode emitting red lights with a wavelength of 650 nanometers. The transmitter uses the LED and receiver uses a PIN photodiode. The physical medium uses the plastic optic fiber. So this is true for MOST 25. So this is consistent with our findings in our bench 2. So from the pictures below on the left, you can see at the end of the orange cable, it's emitting a red light like the MOST cable that uses the red photodiode. And then on the right picture, when we talk about our infotainment system, we located the plastic optic fiber which is black in color. Lastly, we have the automotive Ethernet. So similar to the normal Ethernet, automotive Ethernet is designed to replace or complement CAN bus due to the rising demands for bandwidth. So the increase in usage of multimedia and the upcoming V2X they demands a more bandwidth than the CAN bus. So automotive Ethernet comes in two forms, the 100 base and the 1000 base. And like the FlexRay protocol, it allows for clock synchronization based on IEEE 1588. It supports a bandwidth of up to 1000 megabytes per second, and it's a bidirectional traffic flow. Common applications for automotive Ethernet includes the body and comfort systems, chassis safety systems, infotainment, powertrain, and ADAS systems. So instead of using diagnostics over CAN, for automotive Ethernet, we'll be using diagnostics over IP, which uses ISO 13400 for automotive Ethernet. So in the breakdown on the table on the right, we can see that under the OSI layer, only layers 1 to 4 changes in comparison with the traditional CAN bus. Layers 1 and 2 changes to 100 base and the Ethernet instead of CAN bus. And layers 3 and 4 changes to IP and TCP respectively, instead of the ISOTP protocols. For the physical properties of the automotive Ethernet, single twisted pair wire allows the data to transmit and receive at the same time. And it is designed to reduce the weight of the vehicle. So from the table below, you can see the differences between the standard Ethernet and automotive Ethernet. The length of a standard Ethernet is up to 100 meters and automotive Ethernet is 15 meters. And the connector for standard Ethernet is RJ45, whereas for automotive Ethernet, it can be specified by each OEM varying by model. For standard Ethernet, the cable is two twisted pair and is single direction, while the automotive Ethernet is one twisted pair bidirectional. Next, I'll pass to Alina to talk a bit about the CTF guidelines.
So thank you, Edmund. I hope everybody is still alive after our workshop, and hope you guys picked up something or learned something from the basics for the basics of car hacking. So next up, we are going to move on to the CTF guidelines. So the car security CTF will start from 3 p.m. to 8 p.m. on the 2nd of January and 10 a.m. to 3 p.m. on the 3rd of January 2021. So for the registration, create an account on ctf.carsecurityquarter.org and you will receive an email with joining instructions for downloading and joining the zero-tier VPN networks. So next, create a Twitch account to join the queue on Twitch and join the Discord channel of SINCON and go to the Car Security Kampong channel. And once the teams have registered an account on ctf.carsecurityquarter.org and join a specific VPN network, kindly approach our team on SINCON's Discord channel with the following details to authenticate yourself into the network. So let the Discord admin know the specific network name they will join, your team name, the numbers of players in the team, so a maximum number of 3 players per team, and your player handlers, your player's device address as shown in the zero-tier network, and your Twitch account name associated with the team. Only one account is needed per team. Okay, so next up, once you have placed these details into the Discord channel, the CSQ crew will actually inform you to queue in the Twitch and your queue number. So please only queue for one bench at a time. So to join the Twitch queue, create an account in Twitch and inform your team's username plus zero-tier network details plus the bench you would like to play to our CSQ crew in the SINCON's Discord channel, Car Security Kampong, and go to the specific stream that you are queuing for under the video section of our website. Then type exclamation mark join in the stream channel to join the queue and play. So once it's your turn, the CSQ crew will actually ping you on Discord to join and stand by for the bench playing session. So you will have 30 minutes to play for each bench, and requeuing is actually allowed. So your CSQ crew will inform you on the Discord when you have 3 minutes left. There will also be a countdown timer on the Twitch stream itself. So the difference between the previous CTF and this CTF is that all the questions will be different. So hope to see you guys in the CSQ CTF, and we'll be around to assist you if you need any help. So thank you very much, everybody. And do let us know if you need anything from us. Thank you.